Well, good morning, good afternoon, or good evening, ladies and gentlemen. Welcome to another installment of Unit 3, Biochemistry. Today, we're going to be talking about chemical reactions and enzymes. So, what exactly is a chemical reaction, what we need to have one, and we're also going to talk about the four functions of enzymes and why they're vital to everyday life. So, let's go ahead and get this thing started. I'll see you on the next slide. So, chemical reactions. A chemical reaction is an interaction between two chemicals, where chemical bonds, remember what's holding it together, ionic, covalent, or polar, or not polar, hydrogen, are either broken or formed. So we have two parts of a chemical reaction. We have the reactants and we have the products. So the reactants are what we start off with. So we can have reactant plus reactant to give us a product, or on the flip side, we can have one reactant and break it apart into two products. So chemical reactions and energy. Some chemical reactions release energy. So when we go ahead and break the bonds, the energy comes rushing out. For example, digesting polymers. Whereas some chemical reactions will require an input of energy. You're not going to get the reaction to start unless you put a little something in first. For example, when we're building polymers, so digestion releases energy, building it requires. So chemical reactions continued. The activation energy is the energy needed for a chemical reaction to start. So before we go ahead and get any reaction to actually do anything, we have to go ahead and put a little bit of energy in. We have to put some work in to get the product. So most reactions in our bodies require a high amount of energy to occur quickly enough to keep the cell working properly. So all the chemical reactions in our body need energy. And normally it's a high amount of energy. However, we have something inside of us that helps with these to make sure that number one, we get the job done, and number two, we do it in a cost-effective energy manner. And those are what we call enzymes. So enzymes, these are catalysts. A catalyst, by definition, is anything that causes a change. So enzymes cause changes in our body. Enzymes are proteins that go ahead and do the body's work. And enzymes speed up chemical reactions by interacting with substrates to lessen the energy needed to go ahead and have the reaction occur. So what that does is, we get the same reaction, we get the same payoff, but we don't have to put nearly as much energy into it to get it started. Now, most enzymes have names that end in ASE. For example, DNA helicase goes ahead and breaks down our DNA, it splits it. Lactase breaks down the sugar lactose. So if you see ASE at the end of a word, besides like base, case, face, chances are you're looking at an enzyme. So what we have here is an enzyme, more or less what it looks like. Now, no, not all enzymes look like deformed vampire Pac-Man. This is just an example. So what we do have, though, is an enzyme has two parts. We have the enzyme itself, which would be the Pac-Man shape, and we also have something called the active site. And what the active site is where the enzyme and the substrate meet. As you can see, it fits like a lock and key or a puzzle. This substrate is going to fit exactly into the enzyme. That's one of the big things about enzymes. They're incredibly picky. So they choose only what they want to work with. Certain enzymes only act with certain substrates. So if you would go ahead and draw this real quick, remember you can always pause the video if you need more time. So once you have that copied down, I'll see you on the next slide to explain it. So enzymes, like we said, act on specific substrates. Enzymes have very specific shapes. And a specific substrate, which would be the reactant, will fit into the enzyme's active site. So here, if we go ahead and take a look, the enzyme's active site looks like this. It's a very crude drawing, but you get what I mean. And the substrates here, our reactants, go ahead into the enzyme, and they fit pretty well. So the enzyme and substrate fit like a lock and key. We call this induced fit. So it doesn't fit 100% exactly, but it fits well enough that the enzyme can work with it and move the substrates to where they need to be. So as you can see here, once the enzyme has a hold of the two substrates, it goes ahead, goes through the chemical reaction, changes them, and then spits out the product. So just like before, we went from reactants to products. Wow. Okay, I'm going to be really impressed if you can read that. But anyway, reactants to products with the help of an enzyme. So enzymes primarily work by lowering activation energy. If you think back, activation energy was the amount of energy we had to put into the reaction to get it started. Now enzymes work by lowering this, making the energy cost a lot less. So activation energy is the energy needed to start a chemical reaction, an energy bump, if you will, that you must first jump over to get going. For example, if you were going to go ahead and push a rock down a hill, so let's say you have the rock up on top of the hill, and you wanted to push it down. Now, normally, just by you going ahead and pushing it, that requires a lot of energy. Meanwhile, an enzyme would act like a crowbar, which would go ahead, give you some leverage, and allow you to push the rock down the hill much more easily. So as you can see here in this graph, we have two chemical reactions, one without an enzyme and one with. So this orange block represents how much energy is needed. As you can see, the one with the enzyme is way lower than the one without. So just another example right here. We've got this really weird alien type creature going ahead and pushing a lunar rover up a hill. Why is it doing that? I don't know. It's an alien. I don't understand what they got going on inside their heads. So it goes ahead, we put energy in, and energy is released. One, he goes ahead and tosses it off the hill and breaks a highly expensive lunar rover that probably cost NASA a pretty penny. This alien's a jerk. So, like we had before, we have energy going in to get it to the top, and then the payoff is seeing the lunar rover break. So the alien had to put in energy to get the payoff. Here, this guy would be an enzyme. And apparently he's a giant and doesn't need a spacesuit. But whatever. So he goes ahead, removes the top part of the hill. So the alien has to push it up less to get the payoff of breaking the rover. So same payoff, less energy being put in. So if you would be so kind, we have a graph here, the energy graph, showing how enzymes work and their effect on the activation energy. So what you're going to need to do is anything I put a dot next to, you're going to have to include on your graph. So we need the reactants, without, with, products, energy released, and of course our two lines. So I'll give you a little bit of time to go ahead, copy that down. While you're doing this though, what effect does an enzyme have overall, based off this graph we have? Take your time. I'm going to take another swig of my coffee here. That is fantastic. So, an enzyme. You can pause it if you still need more time. An enzyme goes ahead and reduces the activation energy needed for a reaction to occur, making it occur much more quickly and more cost effective. So enzymes have primarily four features. The first two we're going to talk about are enzymes make reaction happen faster. So they go ahead, they are catalysts, they make the reaction occur much more quickly. And also, reactions do not alter or use up enzyme molecules. So once the enzyme goes ahead, takes in the substrates, goes through the reaction, and kicks out the product, that doesn't mean it's like, well, we used the enzyme, we have to get rid of it. Nope. Enzymes can be used hundreds and hundreds of times before they finally need to be recycled. So, the other two features of enzymes are the enzyme usually works for both the forward and reverse reactions. So, it can work for building something up or breaking it apart. It works both ways like that. And each enzyme has a specific shape and recognizes or binds to a specific substrate. So think of it like this. Remember we talked about Pac-Man. So Pac-Man looks like this, right? Little eyeball there. Yeah, that's the ticket. Now, so as we can see here, the active site, or its mouth, has a specific shape. So, the only substrate he's going to be able to bind to would look kind of like that. And that right there are the four features of enzymes. Now there are some factors that influence enzyme activity. For example, temperature. If you change the temperature, that's going to affect how effective the enzyme is. pH and salt concentration. Enzymes have specific concentrations or temperatures or even pHs that they work the best at. So in the next couple of slides here, we'll talk about that. So what we have here is the effect of temperature. Now, temperature with molecules, this is how it works. A small increase in temperature increases molecular collision rates or reaction rates. So we're going to have things going ahead flying around a lot more quickly, bumping into each other, causing the reaction to happen more quickly. However, you might be thinking, well, what if we go ahead and crank the temperature the whole way up, right? Let's just go ahead and make these things sweat. Well, that's not exactly a good thing. High temperatures disrupt the bonds and destroy or alter the shape of the active site. So if you increase the temperature too much, the enzyme isn't going to work. So as we can see here on the graph, where exactly does this enzyme work the best at? What temperature? Well, it's certainly not 0 to 10. Certainly not 60. There's no activity at those two. So if we go to the top, the joys of drawing with a mouse. So we're looking somewhere between 40 and 50 degrees Celsius, probably around 45. That seems to be the optimum temperature that this enzyme works at. So we have another couple of graphs here, but this time we're looking at pH. We have three different enzymes. We have enzyme purple, enzyme brown, and enzyme red. So which curve most likely represents an enzyme found inside the stomach, and why? Give you a little time here. Now remember, stomach, what's inside of our stomach? That would be stomach acid. And acid, remember, has a low pH. So, which of these would work best? That would be purple, because purple seems to work best at lower pHs. Now, how about an enzyme inside of our blood? What do you think? Now, the blood in our bodies is around neutral. If we think back, 7 is neutral. So which of these works best inside the blood? That would be enzyme brown. So, just a few things to go ahead, and on the next slide we'll just bring everything to a conclusion. But that should just about do it for enzymes, the effect of pH, the affected temperature, and salt concentration will work the same way. So I'll see you on the next slide. So with that brings us to the end of chemical reactions and enzymes. So just in summation, just to go over a few last minute things and summarize what we talked about. First off, chemical reactions. Chemical reactions are composed of two different parts. We have the reactants and the products. So we need both for it to occur. And we also have to put a little bit of energy in most cases, to get a reaction to occur. We have two types. We have reactions that go ahead and release energy, like through digestion, or that require energy, like when we're going ahead and building up a polymer. Enzymes are proteins that go ahead and their basic function is to make reactions occur more quickly by lowering the activation energy. So remember, enzymes basically have four major parts. Number one, they can be used time and time again without having to worry about being broken down. They go ahead and reduce the activation energy needed for it to occur. They're very picky. They only bond with specific types of substrates. And also they can be used for both forward and reverse reactions. So they can be used to create and break apart. Now, one last example I'd like to give you here for enzymes. So consider enzymes, let's say you have to go ahead and cut the grass. All right? Now, we know that what you can do is to cut the grass, you have a lawnmower, you go ahead, you start the ripcord, right? Your traditional push mower. You got to put some energy in to go ahead and get that thing going. And then you have to go ahead and continue to put more energy in as you push it around the lawn, right? Now, an enzyme wouldn't be a push mower. An enzyme would be a riding lawnmower. So you get the same payoff, which is the grass is cut and you get paid, but you didn't have to do nearly as much work or put nearly as much energy into it. Anyway, that's just a simpler way of looking at it if you weren't quite following so far. Now, with that brings us to the end of this video PowerPoint. So, I will see all of you in the next video. Until then, you all keep it classy.